the choice of Python, and that's an important one. There is a new version of Python, and that's 3.8. And in principle, I would recommend you to always use the newest version of programming language. But there were some problems in November, December with the compatibility of 3.8 and the tools that we're using, the libraries that we're using, machine learning library and some plotting library. So if you want to be on the safe side, I really recommend you to use Python 3.7, where we know for sure that the tools work with. Python has a nice property that you can install several versions of it on your machine. So some of you will still have 2.7 from last year's programming course, which I think only worked with 2.7. Some of you might have already upgraded to 3.8. That should be fine if you know what you're doing. And you can always add another version, but then you have to explicitly tell your interpreter to use this particular version of Python to be sure that it works. That is the one where we can guarantee you that it works. So I think these were the two questions that I wanted to share here plenary. Yeah? Okay. So now, for now, we have a bit more than half an hour. I want to get into the notion of agents, and just to be aware of what an intelligent agent is in the first place, but also what we have to take into account when we build an intelligent agent. So that's the first part of the second half, and then in the end, I really want to start thinking about problems of the real world problems in a way in which we can represent them as state spaces, as I called them before, so that we can apply generic AI principles on those problems. Yeah, so it's quite a lot of material I still want to cover. I want to start with the summary and the last slide, because I usually don't get to the last slide with enough time so that everybody's still quiet enough and calm enough to listen to it. So what I wanted to have done today was to give you an introduction of what intelligent systems are, what agents and rationality are, and then what the role of an environment is when you want to build such an intelligent agent. And that is something that will come back again and again through this course. So we have a quick overview over the different types of properties of these environments. Then what kind of agents do you need for different kinds of applications, and how to model problems as state spaces. And the homework, that's the main reason for bringing that. The homework for today is really get a set of cards and try to understand the rules. There is links on the Canvas page. Just follow the links on the Canvas page and try to understand the basics of this game. So intelligent systems, to me at least, and I think it's quite a standard definition, intelligent systems is a subfield of AI which cares about building the intelligent agents. So it's the computer science side of AI, some way, yeah. There will be, at the very end, a philosophical discussion about what is intelligence in the first place. And you might have heard of Turing tests, these discussions, Turing's definition of AI, which all has some kind of problematic, and there has been a huge discussion about how can a field as AI not have a very clear definition of what it is. So what I really want to focus on here is the definition of the rational agent that we're going to build here. And that is an agent that chooses an action, so it's about decision making for an action, given some performance measure in which it evaluates, given the percepts that it has, so the sensoric information that it gets about the world, with some prior knowledge about the environment and the states it is in, to make the best possible decision. So there is an important notion of an expected value performance. So to get to a goal, you have goal states or more goal states that you define, and you want to get there, and the task of the rational agent really develops a strategy of choosing actions to get you as close to those goals as possible. And thinking of an agent we have to think in different levels as well. Because in one way, we have an abstract view over what is it the thing one should do. And that's the abstract function, the agent function, which just has as an input values of some perception and an action as an outcome. So it's a very, very high mathematical level of describing your agent's performance. Then you translate that into some kind of program, and you even have to decide on how to run this on a physical infrastructure. So if we, for example, have this thing, which is a sort of the most simple version of an intelligent agent, namely, I pointed to this, I don't know whether you can see it. So it's a thermostat. Oh, it's not even a thermostat. I can't find the thermostat here. So a thermostat just measures the temperature in the room and decides that below a certain temperature, it starts the heating. Or above a certain, it starts the air conditioning. So there is an abstract way of looking at that, and that is precisely more or less as I described it. It's a function from the temperature to an action, and the action is heating on or air conditioning on. That's very abstract level. Then you have the actual program, and that's a very, very, very hard-coded, simple, stupid program in the machine that sort of says, if temperature is lower than 18, then run procedure start heating, something like that. So that's one way of implementing this function. And then we still have to look at the little box, which has probably a very simple, how is it called? I don't know, my physics is rather rusty. Some physical way of measuring, bringing this information to the CPU, the little computer that's in the box, and that then performs some action in order to get the action taken. Yeah? So there are three different levels looking at those agents. And those agents are in principle just things that perceive from the outside world, and that can be as simple as measuring the temperature in the room and take some actions. And that can be as simple as just raising the temperature or lowering the temperature with the heating. And that is the basic notion of our agents, our rational agents, where they don't necessarily have an explicit representation of the goal, but that is something that is hard-coded in the heating system, and you want to have it at some nice temperature level, but it's still, the thing tries to optimize this. So in a way, this is the first very, very stupid, simple example of a rational agent. But of course, the more complex the problems get, the more complex also the goals become and the way of getting to those goals. So what is rational really depends on the value of the performance measure. So what does it mean to improve? What does it mean to get better given a certain action? What are the actions that we have in the first place? What are the choices we can make? Have we gotten any experience, any data that we've seen before, any measurements that we've seen before that we can use? And do we have any extra knowledge about the world and about the environment to which we can apply our intelligent agent? And of course, if we have the heating system, it's so simple that all this doesn't play a role. But if you have a self-driving car, this is a completely different story. So nobody expects the rational agent to be omniscient, know and everything. That's not how things are in the real world. We humans are intelligent. We are rational without seeing everything happening, knowing everything that's going around. And it's never about perfection. It cannot be about perfection. It is about being as good as possible. And this depends very much, yes?
Yes. What does the word omniscience mean?
Not knowing everything.
Okay.
Yeah. This all depends very much of the environment in which we work, of course. So there is no, yeah, sorry? Knowledge representation. So if we want to design such an intelligent agent, we need to understand very well in which environment it performs. So what is it doing? What does it need to do? Where is it going to do it? How does it do it with the actuators that it has? And what is it perceiving? What information does it get from the outside in the first place? And that's a sort of a standard exercise that one should do when you build an intelligent agent, that you take those P's criteria about your problem that you want to solve and study this. So if you, for example, want to build a self-driving car, a self-driving taxi in this case, that collects people at the airport and drives them to some hotel or so, it needs to be able to perform in a safe way. It has to land. It has to be on streets. It needs to reach the destination. It needs some profit, so it needs to be cheap to go. It needs to be legal, comfortable, and so forth. So there are loads of criteria that your agent needs to fulfill. And the environment is, in this example, of course, a very complex one. It's traffic, it's other people, it's pedestrians, it's the weather. Think of whatever has an impact from the outside to the agent. The actuators that the thing has is the steering, of course. You can go left and right, the speedometer, it can accelerate, it can brake, it can horn, whatever. It can sometimes speak. And it has a lot of information that it can collect. But if you make an analysis of a problem like this, then you see that your intelligent agent needs to have a very, very complex decision process. So we're looking at things that are far easier and far simpler to look into. And we look at particular different environment types of which we understand what kind of properties they have. And I use some of them already in the first half of the lecture, like, for example, the single agent one, or I think the deterministic one. I use the uncertainty that you have about the next situation. I used the observability. That was the one I used. So what does observability means? Can I fully see all the possible states of the environment? Do I know everything about the environment that's relevant for my problem? And of course, in Schnapsen, our Schnapsen game, it's not fully observable, because I do not know the cards of my opponent. In chess, for example, I see the full game. I see in which state I'm in. So this is the distinction between observable and non-observable situations. And if you look at those different cases where the first one is a solitary game where you play on your own some ordering of cards. What's happening here? Nothing's happening. Why not? Oh, that's good to know. So solitary is fully observable. You see all the cards. You know what's happening. Backgammon, even it's a game with chance where you where you have to throw a dice. You know exactly where all the possible stones are on which part of the field. So it's fully observable. If you have a shopping assistant that wants to help you to find the cheapest shoes on the internet, that's not the case, because the shopping assistants will never know all the shops in the internet. So it's a tricky thing. And the same with a taxi. Of course, in principle, it can see everything, it can smell, it can, as humans do. But in practice, this is not the case, because there's so much information that is impossible to fully observe. Deterministic versus stochastic. The question is, when I play a chess figure, then I know exactly to which state I get, what the next board position is. In some cases, this is not the case. So if I have backgammon, for example, I do not know in which state I will end up, because the next time my opponent turn it is, he will throw a dice, and I don't know which of the possible positions I'm going to be in. And the same with the taxi. It's absolutely impossible to really know where, after a certain action in the state space, I am. The next kind of problem is static versus dynamic. So is the game environment, for example, changing between situations? So if I make a move in chess, does anything change about the game? No, it's a static. It's a static game, like solitary, for example. Same with the gammon. The board is exactly the same afterwards. But if you are in a taxi, then 100,000 of other factors change constantly in the environment. So that's also a very important distinction between different types of environments. Discrete versus continuous. Do I have just a small number of actions that I can take? And are there certain small classes to which I have to decide my problem belongs to? Or could it be just a continuous number that I have to decide on? Driving, for example, of course, you don't drive only to the left, but you drive to the left to a certain degree. And how big this degree is changes the way that the next state is. So it really depends on, in this case, continuous values that you're going to take, both in the sensing, but also in the acting. Oh, that was the one I just said. And then, of course, is it just me in the world? So if I play solitary, then, of course, it's just me, nobody else intervenes, and I just follow a strategy to win the game. But if you have the gammon and all the other examples, you always have other people in your world, sometimes competing, like in backgammon, sometimes just doing their own stuff, not necessarily being opponents or adversaries. Yeah. So this is not so much about the details. So I think whenever you build your own system, your own intelligent agent, you need to analyze a situation. And that is not something new, but this is sort of a cooking recipe that you can follow in order to try to understand what are the different factors that have an impact on my agent, and how do I circumvent specific problems, or how do I build my system so that it really is suitable for this specific environment. So if we go for Schnapsen, of course, we have non-full observability, and that's the big problem with Schnapsen, that we have these 14 cards of which we don't know where they are, basically. It's static because nothing changes. The cards are, in the beginning, they are distributed once, and after that, they are all in the same position. It's just that I get more information the further the game is. It's discrete because there is only a finite small number of moves that I can take at every state, and it's very clear. So I can play the Queen of Hearts, but I can't play it half or a third or a quarter. And it's not single agent because I have someone else to play against. And this person is very much adversary because she or he wants to win as well. Deterministic is that once you make a move, you know exactly which position you are in, which new situation you're in. And maybe you don't know it, but you always end up in a fixed situation. So there is no dice, throw the dice in the middle, or no element of chance. So if you now, most of the games are, if you have poker, for example, and you take a new card, in a way you can say that this is not determined beforehand which of the cards you get. And here you always, it's all distributed, they're all in a pile, there's a certain order. Once I make a move, there's always one solution to get to. There was one more question here? Same question. Okay, that's always good. Yeah. Yeah, but in the pile in Schnapsen, the pile is in a certain order, and the order doesn't change anymore. So it's fixed in the beginning of the game how the game will be played. If you would if you would remix the cards after some move, then you would become non-deterministic. So, yeah.
So for Schnapsen, isn't it partial observable? Because after 5 moves, I can see whole.
Absolutely right, yeah. So in the second phase, the game moves from an imperfect information game, which is not observable, to a fully observable game. Yeah, that's a very, very good point. Which I think is the one that makes it so interesting, because you really have to apply you live in two different environments in this game. Yeah? Okay, now we had and I really want to be quick here because in a way this is relatively clear stuff, but it's good to just mention it once so that you're aware of the differences that you could look into. Tomorrow we are really getting more technical, more algorithmic, more concrete. Here this is more abstract overview to have you give you an impression of how you can look at these agents in different ways. And one thing is this, the different types that your agents can have, and that starts from the very simple ones that I mentioned before with the heating, which is just called reflex agent. And the only thing it does is that it perceives something and it has some rules, some condition action rules. If temperature is lower than, do this action. So it's a very simple, it's just a reflex. I get some information and I have no information about the state. I don't know what is going to happen after I increase the heating. I just have those rules. That's all I have. Yeah. The more interesting, so there's always and that's quite nice in the book and also in the reader. For all the intuition that I explained, there's always some pseudocode. And it really makes a lot of sense for you to look at the pseudocode later. And I don't want to go through all the pseudocode in the lectures themselves, but it is in the slides as well. And then you can see how this simple reflex agent is implemented on a very high level. And you will see then that, okay, of course you can use such a system for a heating, that it needs to be adapted a little bit, but it doesn't work in many, many cases. Particularly if you have only partially observable environments, then you need some more information about where you are, what is the situation I'm in, what is the state of the environment, and what will be the effect of what I do. So you have now some state information, so they are now called reflex and state agents. You have the information about the state of the environment in which it is in. How is the world going to evolve? What kind of actions do I have, and what is the impact of those actions? And then basically you look at those rules based on the state description that you have, and you make a decision then on the basis of, okay, now I switch on the heating because there are 70 people in the room, so I need more information, I need the state in which this environment is in, and then I can make a certain choice for another simple condition action rule. Still very relatively simple type of agent. The only thing it does now is that it takes the state of the system into account. There was up to now not an explicit definition of the goal that you want to achieve. So you might have different goals. For example, if we look at the previous agent, which just has some state information, but not yet what it wants to achieve. So if you have the information that you want the temperature to be between 20 and 21 degrees, then you can make plans taking into account the number of people who are now here and the number of people who will leave and how this will be in half an hour, because then the room will be empty, and these kind of things. But then it is about a specific rule that's explicitly modeled in the agent. And then, of course, all these kind of agents we can equip with some kind of learning. So we could also tell the agent, okay, yesterday we had a similar situation with so many people in the room, so now you should not make the mistake of increasing the temperature, because now in 15 minutes everybody will leave and then the room will be too warm. So I've learned that from the experience from yesterday. Of course, you can do that for all types of agents. Yeah, and we can basically see the same when we do the Schnapsen. We can implement very, very simple reflex agents, which just says if it's my turn, not even knowing anything about it, then I always play the smallest cards, the cheapest card that I have. Always go for the jack. Yeah. It doesn't know anything, it doesn't need to understand, it just always plays the jack, and then it plays the queen, and then it plays the king, and it will always lose, of course, but it would be a strategy for a simple reflex agent. Then you can increase that up to levels of where you have a lot of knowledge, and we have learning involved. Yeah? Okay, so I mentioned that word quite often. So let's spend the last 10 minutes on the notion of the state space. state space representation and then the state space search. And the search is actually quite simple. Tomorrow we'll see that. But what is a challenge is to see how can we represent different types of real-world problems in one generic framework, so that we can also apply generic algorithms later, because that is what we want to do in AI. We want to find generic solutions for many, many real-world problems that all function efficiently and well understood. So here is a simple example, which is also quite complicated if you think about it. That's an automatic Hoover. So it doesn't do a lot. But it's still quite complicated. So it moves in many, many directions. It has decisions of hoovering or not hoovering. It can move at different speeds. So it can be modeled in a very, very complicated way. But if we have a problem where we just say, okay, we have enough time, don't care about how fast things are, but we have two rooms. I want to make sure that in these two rooms, at the end of the day, both rooms are clean. How can we have our Hoover? How can we simplify this problem in a way that it becomes a generic problem to which we can apply some simple decision making? And there's basically a very, very simple way of representing that. And this is a problem where we have two rooms. We might have dirt in the room. We might have a Hoover in the room. And we might have some simple action, and that is Hoover going through the room. And then once the room is clean, you can move to another room. And of course, the decision of when to go to the left and when to go to the right is very simple for humans. But if you have an automated agent that does the decision itself, it's already not that trivial. Yeah? But this is now a simplification of the problem, which is a sort of graphical representation of a state, namely a state in which I have two rooms, two of them are dirty, and on the left-hand side, there is a Hoover. So now that would be a state. The question is now, how can I represent this as a state space? So give me all the possible states that I have, and give me all the actions that I could take from moving from one state to another. So we are trying now to get from absurdly complex problems, like the Hoover deciding on moving 45 degrees, 45 degrees, 46 degrees, which direction should the Hoover go, to the very, very simple problem of the decision making that we want to make here. Namely, how do we get the two rooms cleaned on the decision moving from one room to the other? And that's all we do here. Yeah? So what we built is a set of states, and these states map to real states in the world, but we don't care where exactly the agent is. That doesn't matter, as long as it's in the room and as long as it can clean the room. And then we have a map to change from one state to another that is similar as to a state in the real world. And our solution is just a set of actions that we can then have applied on the agents themselves. And there might be different state representations. So this is a simple one, the graphical one, but you could also have a mathematical representation of this state space. And then if you go back to this vacuum cleaning world, then you basically see that there are 8 possible states that our world can have. And for each of those states, we have some ways of moving from one of the states to another state. So if we are in the state that we had just before, where we have dirt in both of the rooms and the Hoover is on the left-hand side, we have the actions for the Hoover is either cleaning the place, moving to the left or moving to the right. Moving to the left, if you are on the left, obviously it doesn't change anything. So that is this one, moving to the left gets you to the same state. But even if you move to the right, so that was this one here, if you move from this state to this state, if you move to the right with the Hoover, then you get to this state. And this is just a graphical representation of all the possible actions that my my machine can take, namely going left, nothing changes, going right, going here. Sucking, cleaning the room gets you clean here to the right. If you suck again, nothing happens. If you move to the left, you get into this state. If you suck again, you get into one of those states, and this is a state where both rooms are clean. Yeah? So it's now a very simple representation where I have a systematically enumerated all the possible actions that get me from one state in the world to another state in the world where now we have a solution, where we reach the goal of 2 clean rooms. And this kind of representations we can now apply to many problems. And once we have such a representation, we can also systematically try to find a path from this situation to one of the goal states. And the path, the solution to the problem, is just the enumeration of the actions that my agent has taken. Yeah? So we need to represent our problems in a way that we decide on what the appropriate states are. What is the initial state? Which state do we start with? What are the goal states? Sometimes you need to take into account the cost of the actions. Sometimes you have one goal state. Sometimes you have more of them. So if you play chess, for example, all the goal states are the one where I chessmate my opponent. But there could be, of course, hundreds of thousands of different board positions where I chessmate my opponent. And then what we're going to start looking into tomorrow is that once we have this representation, how can we search for the best, or maybe in the beginning, a path from the initial situation, the initial state to the goal, to one of the goal states. How can we search for that? Once we found such a path, we can obviously execute it then. So we have all the actions that we take in order to go to a chessmate state, which means just following, setting the things in the real world. As we would say with our intelligent agent that hoovers the 2 rooms, if we have an action L, we just translate it in our agent program to, now you have to move from this room to the other room, and you have to clean and translate the actions back to the real world. And you can think of many examples where you have a robot arm, and the robot arm is in a certain position, and this position defines a state it's in. So it is in a certain rotation degree here, it has a rotation degree here, it has an arm that it can stretch, it has some more rotation here. All of those are possible positions it can be in. And this is now not a discrete environment anymore, so it has continuous values, so the rotations can be different. So we are already now looking at many states, depending on the measurements, possibly infinitely many, but still we can represent it in exactly the way. So we just have a value for this, and this. And if you now have an action of, for example, extending the arm, it's just that in your state representation, the p-value changes. But still, there is the same thing. We move from one state to another one, although it's far more difficult, of course, to write down. So if you want to build a state representation, you just have to sort of abstract the problem itself. What do I want to achieve? I want to clean both the rooms. So I want in my state representation both of the dirt values to be 0, for example. You need to formulate a concrete and algorithmic goal. So that is in the real world, that is the house should be clean. And in the state representation, it should be, I need to be in state 7 and 8, because these 2 states in the bottom, they have the cleaned room. And then I need to find the solution, and the solution is finding the sequence to get from state number 1 on the top to one of the states on the bottom. And then in the end, my agent executes the plan once I found the way from 1 to 7 or 8. Another example is a map. If you have a map, you know this is the map of Bulgaria. You want to be, for example, you're in a city like Arad, and you want to Bucharest. And then the question is, what is the best, the shortest path to get from Arad to Bucharest? You represent your map as a graph, like we did here. This is already a state representation, because in the real world, it's absurdly complex to get from Fagaras to Bucharest. And all we've done here is draw an arrow and have some information about the distance, the aerial distance that you might travel. And in real life, you have to rent a car, or you have to go to the train station, and then the train makes a very complex journey. We simplify this because this is all we need. We want all the information about how can we find the shortest path between Arad and Bucharest, based on the knowledge that we have to travel 211 kilometers between Făgăraș and Bucharest, and it doesn't matter whether we do it in turns or whether we stop in the middle. It's just the distance that we want to know, yeah?
Is the map itself already in the state space, or are all possible routes from A to B?
Now, this would be this is a state space representation. You would have the representation that I'm here. That would be the state. So if you want to travel from Arad to Bucharest, being in one of those places would be the state. Yeah. So this is a concrete problem, is that I need to have a flight tomorrow from Bucharest. I need to travel from Arad. I have the trains. My states are the cities in which I could be at a certain time. The action is driving between the cities or moving between the states. And then the concrete goal is I will be in Bucharest in a game that would be, I will be in a winning node. Finding the solution is the sequence of states in which I travel. So I travel from Arad to Făgăraș and so forth. And then in the end, once I have this decision made, I can translate this back into the physical world by buying the tickets and travel via the decision that I have taken. And then the last slide before we finish, if you now look at games, because quite a lot of this first lecture was about games, you will see that this is exactly the same. So you have a state you're in Go, for example, and then there are loads of other states that can reach from the position you're in. And in principle, what we're now looking into tomorrow is finding a path. What is a short path between one of the initial situations I'm in to a winning position, like you would here in chess, from the starting position you're in to one of the winning positions where you can checkmate your opponent. And we're looking into that tomorrow morning. I don't know what time the lecture is tomorrow. And that was it for today. So enjoy the Schnapsen.